Hi there, this is Saman and you're watching the Genesis YouTube channel. In the last video, I left you with a 10-part variant of the triangle pursuit problem. I hope you have tried that. Today, we'll go ahead with the solution to this problem. Before we begin with the solution, we need to be clear with certain things which will help us in the solution. First is the motion of a particle in the plane polar coordinates and how do we write the velocity there. Now, firstly, the position of a particle can also be given by plane polar coordinates r, theta as shown here instead of x, y. Now, to analyze the motion, we identify two directions which will be crucial for us. The first is the positive radial direction, which is in the direction of increasing r. The second is the positive transverse direction, which is in the direction of increasing theta. These are perpendicular to each other. Note that the transverse direction is not the same as tangential direction. Here velocity is along the tangent. The velocity vector is along the tangent. The transverse direction in general does not coincide with the tangential direction. Here we resolve the velocity into two components, Vr and V theta. This is very much like Vx and Vy. When we resolve along x-axis, we say Vx. When we resolve along y-axis, we say Vy. Here, when we resolve along positive radial and transverse direction, we say Vr and V theta. In this video, I will not be getting into the proof for the expression for these velocities. Rather, I'll be trying to give you an intuitive feel of what these velocities are doing. Now, as the particle moves, its position vector changes. And this position vector changes not only in magnitude, but also in direction. So we can say the position vector can stretch or compress as well as turn. Now try to imagine if you only had this VR. If you only had this VR, then the particle would have moved in a straight line, increasing or decreasing only this coordinate r. Therefore, VR is responsible for only stretching or compressing the length of the position vector, and therefore obviously its value is dr by dt. Now try to imagine if you only had V theta and no VR. In this case, the particle would go in a circle, and therefore this expression for V theta omega r should be apparent. Understand that this is not a proof, but this is how we try to understand what these components are doing. The radial component of velocity is either stretching or compressing the position vector, and the transverse component is turning it. So the radial velocity is the stretcher and the transverse is the turner. To write it in vector form, we take a unit vector like this, which is called the radial unit vector. And its direction is in the positive radial direction. And another unit vector in the perpendicular transverse direction, and obviously we call this the transverse unit vector. So the velocity vector can now be written as dr by dt er cap plus omega r, this omega I have written as theta dot, which is d theta by dt, into r into e theta cap. This is nothing but something like v vector when we write dx by dt I cap plus dy by dt j cap. So here along er cap the velocity is dr by dt, and along the transverse direction it is nothing but d theta by dt into r, or which we simply write as omega r. So I repeat again, the velocity can be decomposed into two components. First, the radial one, which is increasing or decreasing the length of the position vector, and v theta, the transverse one, which turns the position vector. In addition, we also need to understand what the components of acceleration do. Now, the acceleration vector can be resolved into the tangential component and the normal component. Remember that velocity vector is always along the tangent, and therefore the expression tangential velocity is an idiotic expression. Why is tangential velocity an idiotic expression? If I ask you your name, you do not say my name is human being so and so, right? So similarly, velocity can only be along the tangent, and specifying tangential velocity is as idiotic as saying human being so and so. Now going ahead, acceleration vector can be resolved into two components, AT and AN. Along the tangent, AT, the tangential acceleration; along the normal, AN, the normal acceleration. The tangential acceleration is the one which changes the speed, and the normal acceleration is the one which changes the direction of velocity vector. And the expression for this, in fact, if you see, the tangential acceleration is given by dv by dt. Now this is indicative of the fact that tangential acceleration is the speed controller, or the controller for magnitude of velocity, whereas the normal acceleration is the one which changes the direction of velocity vector. So here tangential acceleration is the stretcher for velocity vector, and normal acceleration is the turner for velocity vector. I hope that is clear. Normal acceleration is given by v square by radius of curvature. V speed at that point square divided by the radius of curvature at that point. Now coming to our question. This figure shows the situation at different time instants, and this shows that the particles are always at the vertices of an equilateral triangle which is continuously diminishing in area and rotating, and finally this area is going to vanish to zero. Each of the particle is moving like this. Now in this, there is one very interesting thing to note. Suppose I consider one of the particles, say this one. These are the locations. Can you see that it is always on the vertex of an equilateral triangle, and its velocity is along the side. It is always directed towards the other one. So we can always say that the angle between velocity vector and the line joining the centroid to this particle is going to be 30 degrees. All the particles are going to meet at the centroid, and at any given instant the velocity vector is along the side, and therefore this angle between the velocity vector and the line joining the particle to the centroid, this is always pi by 6. This is maintained throughout, and this is what we'll harness in this solution. This is the situation with the conditions given in the problem. This is our initial line with respect to which we will measure theta, and this particle initially was here. Now it has come to a location here. Its velocity vector is making an angle of pi by 6 with the line joining it from the centroid. Its location at this point is r and this theta. So this location is r comma theta. Now you can see that this is the positive radial direction, and this is the transverse direction, the positive transverse direction. Accordingly, v vector has been resolved into the radial velocity and the transverse velocity. It's clear that the radial velocity is v cos pi by 6 and the transverse one is v sin pi by 6. So accordingly, I have written, if I take the unit vectors here as the radial unit vector and here the transverse unit vector, then the component VR is inwards, which is opposite to this unit vector. So minus V root 3 by 2 ER, and in this direction it is along the positive transverse direction. The transverse velocity is along the positive transverse direction. So V by 2 E theta. Compare this with the standard result. V vector is equal to dr by dt ER plus r d theta by dt E theta. If we compare this, we get two equations. dr by dt is minus v root 3 by 2 and r d theta by dt is v by 2. Divide these two equations and take d theta on the other side. We can integrate this expression. When the particle was here, the value of theta was 0 and the distance from the centroid was L by root 3. When it is at this position, at a general position, the value of theta is some general theta and then the value of r is some general r. Integrating this, you get an expression like this. This is the polar equation of the path. Taking this equation again and separating out the variables, I can now integrate at t is equal to 0, r was L by root 3 and at the time when it reaches the centroid, the r value is 0 because it has reached the centroid. Centroid is the origin. This gives us the time at which it reaches the centroid as 2L by 3V. So the three particles meet at the centroid following this path and take this much time, 2L by 3V time, to reach the centroid and meet each other. Let us focus now on this path equation. This path equation is of the form r is equal to a e power minus b theta, where a and b are constants. I can write this as a divided by e power b theta. Now, a little reflection will show you that at theta is equal to 0, the value of r is a, and if I keep increasing the theta, the value of r is going to decrease. And this is going to trace out a spiral like this with infinite number of turns. Why infinite number of turns? To make r 0, theta has to go to infinity. Theta is equal to infinity means it is turning infinite number of times. This kind of a curve is called a logarithmic spiral. And logarithmic spirals are found everywhere in nature, from flower patterns to shell patterns and so on and so forth. Probably I will make a video about that sometime later. Now coming back, this equation therefore represents a curve which looks like this. And how many times does this particle move about the centroid? How many turns does the path have? Infinite. Therefore, each particle is turning infinite number of times about the centroid before actually reaching the centroid. Now you might have a question that if there are infinite number of turns in the path, how come the time is finite? Understand that just because one parameter of the motion is infinite doesn't mean that all the parameters of the motion will be infinite. The inner turns are executed with extremely high angular velocity so that the time of turning in later turns becomes extremely small, and when added to the whole time contributes very less, and it kind of goes into a series which basically converges and gives the value 2L by 3V. Next, the displacement of the particle. Now you can see that the particle starts from the vertex and reaches the centroid, and this distance is the displacement. This shows the red one shows the displacement, and that value is L by root 3. Now although the path has infinite number of turns, the distance traveled or the length of this path is not infinite. In fact, it is very easy to calculate. Since the motion is occurring with constant speed, the distance traveled is simply speed into time. So v into 2L by 3v, which gives us the answer s is equal to 2L by 3. So the distance traveled or this length of this path having infinite number of turns is finite, and that is 2L by 3. Magnitude of average velocity is displacement by time, and you can straight away see that it is going to be root under 3v by 2. What is the average speed? Average speed is just v because it is motion with constant speed. If the motion is with constant speed, then the average speed and the instantaneous speed match. If this is not obvious to you, then you calculate the average speed by doing distance by time. Distance traveled is 2L by 3, time is 2L by 3V, you will get an answer of V. But you really don't need to do this calculation because here it is clear that as the speed is constant, the average speed throughout is going to be V only. Now coming to the calculation of acceleration. Now let us say in dt time, the triangle turns and these particles reach here. So in dt time, how much distance will each particle travel? V dt, right? And let us say that the orientation of the triangle has changed by d theta. So nearly how much is the edge length left? It is L minus V dt. Now you can see from here that the velocity vector will also turn by the same amount d theta. And its magnitude is same, so the length of these two sides is same. Therefore, this change in velocity dv vector has a magnitude of v d theta. This simply follows from arc length is equal to radius into angle subtended. Therefore, the magnitude of acceleration is given by mod of dv vector by dt, which is v d theta by dt. Which means to find the magnitude of acceleration, I should be able to find out this quantity d theta by dt. To calculate d theta by dt, focus your attention on this triangle. Now here you can see this angle is 60 degrees. And I have drawn an arc so that this length and this length are the same. So this is nearly 90. And therefore this green part is nothing but v dt sine 60 or v dt root 3 by 2. Now you can see this green part is the arc length, L minus v dt is the radius and d theta is the angle, and therefore we can straight away write v dt root 3 by 2 is equal to L minus v dt into d theta. Arc length is equal to radius into the angle. Now when you multiply this, you multiply d theta into this expression, you will see that the second one will give you a product of infinitesimals dt into d theta, which you can neglect in comparison to L d theta. Doing this will give you d theta by dt as v root 3 by 2L. Substitute this expression here, and this gives you the acceleration magnitude as root 3 v square by 2L. So this is the magnitude of acceleration, total acceleration at t is equal to 0. And now the rest of the answers are extremely simple. The tangential acceleration of the particle is 0 because the speed is constant. So A tangential is 0, therefore the total acceleration is nothing but normal. Therefore we can assert that the acceleration vector is perpendicular to the velocity vector. The total acceleration is normal at the initial instant. In fact, throughout the motion, only the normal component of acceleration exists. The tangential acceleration is throughout 0. Now, as the tangential acceleration is 0, the normal acceleration is root 3 v square by 2L. And the magnitude of the acceleration is root under 3 v square by 2L. So these are the three parts. Now, the normal acceleration is root 3 v square by 2L. Also, the normal acceleration is v square by the radius of curvature. So, equate these two and you will get the radius of curvature as 2L by root 3. This is the radius of curvature of that logarithmic spiral at the initial instant. The next part requires us to calculate the accelerations at a time t is equal to L by 3v. To do this, we note that the relative configuration of velocities of any two particles remains the same. That is, one velocity v is along the edge and the other one is at an angle of 60 degree to it. This implies that the relative velocity along the edge is always v plus v cos 60, 3v by 2. That is, this edge length, this length is decreasing at the rate 3v by 2. Therefore, the instantaneous length of the edge is nothing but L minus VR, which is 3v by 2 into any time t. So we want the situation at L by 3v. So the edge length at that instant is L minus 3v by 2 into L by 3v, and therefore we get the edge length at this time as L by 2. That means at this instant the particles are on the vertices of a triangle whose edges are half of that of the initial one. Now after this the situation is very simple, because everything that we did for t is equal to 0 with the edge length of L now can be done at t is equal to L by 3v with an edge length of L by 2. That is, tangential acceleration is 0, normal acceleration, all the same calculations hold, only difference will be this time the edge length is L by 2. So this is your normal acceleration. Total acceleration magnitude is obviously the same, and as the normal acceleration is root 3 v square by L, and it is also written as v square by rho, so the radius of curvature at this instant will be L by root 3. This concludes the solution to this problem. So if you like this video and learned something from it, like, subscribe and share widely amongst your friends. And as always, till the next time, stay safe and stay healthy you all.